accepted, challenge accepted. The attitude is always challenge accepted. Challenge accepted, challenge accepted. The attitude is always challenge accepted.
Winter tires yet? Because Kiril is about to give you some traction on the topic.
Please applaud
Kiril Vuchkov!
Everyone. See more people coming in, so that's good. Yeah, today, thank you for the nice introduction. Today I'm going to talk to you about how to break the ice, how to build reliable and efficient and effective communication between services in a system that is distributed. So what to expect today, and why do we need to break the ice between services? Why there is ice in the first place? Turns out services are quite shy. They don't want to share too much with their clients, and actually we need to do something. We need to take action to fight that introvert of services and help them talk to each other. So I'm going to take you through a journey, right? How to bring a distributed system into production, and focusing on, of course, service-to-service communication. This journey starts with a choice. You have to figure out what is right for your use case, what is right for your clients in terms of the API that those services needs to implement. How many of you working on RESTful services, RESTful APIs? Or have worked? Okay. How many of you have worked on gRPC or used gRPC? Okay, not a lot. So just to outline the main difference, REST uses HTTP and JSON to communicate between client and server, and the API is modeled with as a set of resources that accept different methods. So like verbs like post, delete. So it's very much modeled around the web as a kind of hypertext style, almost. gRPC, on the other hand, is an RPC. Everybody alive? Okay. gRPC, on the other hand, is an RPC protocol, which means that it works by creating client objects that look like a local object, but when you call it from a client, it actually invokes a procedure remotely on a remote process. And for this talk, I'm going to focus on gRPC, so bear with me. So we decided we want to use gRPC. It's nice, performant, good support, and has some nice features. For example, runs over HTTP2. It uses binary encoding, so it's efficient, so we like it, and we start working it. So if you take a look at the gRPC website, there is a getting started. I will not walk you through that, but basically what we do is we write the schema, we generate some code, we bootstrap a service, and we implement a service interface that is generated by based on the schema, and then we have a container, which is our service, which has an API. If we look a little bit closer, how does this look like? We start with the schema. So this is schema. gRPC is schema first, which is quite handy. We can get it reviewed, etc. And then based on this protocol buffer description of our service and the messages that it accepts and returns, we write the green parts, essentially, the business logic and the handler. And everything else, as you can see on this diagram, is kind of done for us. So we get the code-generated structures, we get the which are passed to the code-generated client called a stub. Then this goes to the gRPC channel, which is the abstraction of this connection to an endpoint, to a remote service. And then this serializes the request using protobuf, sends it over the wire. And then on the other end, essentially the handler receives the same object, the same message that was passed to the client stub on the client side. That's kind of magical, if you think about it. So this is the request path. And then we have a response path. So how does this response path look like? We have a handler. The handler returns like as a normal function return. And this goes through a similar process as the request. So it's serialized, it's transported back to the client when it's deserialized, and then the business logic on the client side, it actually sees the response object. Again, kind of magic. There is one additional thing, which is called the status. A lot of you shared you've been working on REST, so it's entirely similar to the HTTP status, so there is some semantic attached to those status codes. You have unavailable, you have not found, invalid argument, so kind of there is like a nomenclature with those. So that's it, pretty simple. Before we decide to do something with this container that we have, one tip for the day is to enable server reflection. So what does this mean? How many of you are kind of have an API, because most of you said you're doing REST, how many of you are publishing like Swagger or OpenAPI on those services? Okay. So yeah, what it does is essentially it allows your client to see, first to discover your API. So they can browse your API, they can see what methods, what objects, and there are a lot of tools that support that discovery. And what is even more awesome is that what they discover is not something in a source control that they don't know, okay, is this deployed on this instance, in this environment. They actually can see what is live currently, what the server's perception of the API definition is, which is quite powerful. And a few tools that I mentioned here, there is gRPC URL, or I'm not sure how you pronounce that, but it's like curl for gRPC. You can send requests from a CLI. Postman, I guess many of you have used. There is one more, GHZ, which is essentially a load testing CLI. It's quite simple, quite powerful. You can use it as a CLI or as a library. Those things are much simpler when you have the reflection enabled. So, okay, we're ready. We've played with our container. It works well. We tested it. Everything cool. We want to deploy it to AWS. And turns out AWS loves gRPC. So it's quite simple. You read the documentation. It's good documentation, good community. It's fairly simple. You deploy your container, let's say in ECS. You then provision also a load balancer, and this load balancer connects to your services, integrates. You can integrate it easily in the DNS service. And then what happens is that we have a client uses DNS to discover the load balancer by the name of your service, sends a request, requester TLS terminated, so you get kind of certificate security. You get black box metrics, so load balancer publishes those metrics, so you can build your dashboards for latency, for failure rate, you can have your alerts, and it's kind of independent of, like, if you have a bug in your code, like those black box metrics still there, they will catch it. It works with bridge mode. This is a little bit, again, like a more advanced tip. So if you deploy your containers on, let's say, an EC2 instance, there is a limitation on the number of virtual interfaces that you can attach to it, or you either, and if you want to use the same port number for, let's say, all your gRPC services, it's a little bit tricky to get it. And AWS Load Balancer, what it does is that it allows you to use bridge mode, so like your services are hosted on the same machine, they're exposed through different ports on the host, but the load balancer kind of abstracts that. So for your clients, let's say all gRPC services are always on the same port, like on the same standard HTTPS port. So yeah, it works quite nice, and also we get AZ failover, availability zone failover if we need it. And everything works nicely, and we're super happy. We let some clients in, and then failure happens. And what should we do in that case? I mean, this is service unavailable. There is like the same code, equivalent code in gRPC status codes. And it's pretty obvious. If you see that, you probably want to retry, right? I mean, it's kind of obvious. This is what you do. However, not all errors are equal. What about not found error? How many of you think that a client should retry a not found error? Okay, 0. How many of you think a client should not retry a not found error? Okay, we have a few neutral people in the room. The simplest approach is to say, yeah, not found error, it's not there, right? But if your service has any kind of eventual consistency to it, it might turn out that you can essentially you might want clients to retry not found error. So there are those services that can do that, right? But this makes it super complicated because what should a client, imagine that the client service is done by another team, right? So they see those not found errors, and what they do is they come banging on your door and they ask you, okay, what should I do, right? I just keep seeing those not found errors. You have a bug in your service. And we say, no, we don't have a bug in our service. Our service is super scalable. There is eventual consistency. If you just try again, like 1 second later, you will see this object. Like, no worries, right? And this communication is extremely inefficient. We don't want to do that. We want the services to talk, not necessarily the teams. Of course, the teams can discuss weather and sports, but regarding what you should do with errors is not the best conversation topic for like the water cooler. So essentially, we need a way to tell our clients what to do when they see errors. And in gRPC, there is a mechanism which is quite robust. It's called service config. So basically, I can describe, as a service owner, I can describe how clients should treat my errors. And what is more awesome is that this is implemented on the gRPC client across languages. So any gRPC client, like standard gRPC client, can understand the service config and will honor it and will know without somebody banging on my door that not found errors for this particular service should be retried. And maybe internal errors, which is like 500 equivalent, should not be retried or should be retried. Like really depends on the case. And we have the mechanism, we have empowered service owners to tell that to clients, to broadcast that to clients. We can also tell clients how many times to retry. One little caveat, the Golang's gRPC implementation actually has a hard-coded limit of 5. So you cannot configure in your service config more than 5 max retries. But yeah, let's move on. We've done that, we've seen that, and then we also need to tell clients for how long. So we can say, okay, our service might experience some failure, and if it happens, if it's transient error, because we told you what is transient error, like let's say unavailable and not found, if it doesn't appear in 15 seconds, don't bother. Like it will not appear ever. There is something else going on. And this is a very powerful mechanism to say. But you might ask, okay, what happens if I have a client that's kind of customer facing? So like somebody presses a button. And then I have a chain of services, and somewhere in the chain of services, I have a service that says, okay, retry for 30 seconds. Like, would the spinner just go on and on for 30 seconds? I mean, hardly ideal user experience. Luckily, gRPC has quite robust deadline propagation, which works by default, so you don't have to do anything special about it. If I have a client request, so every client request sets the deadline and says, okay, here's the request, and I would expect to get the answer by that time, right? And then the service accepts that, and if the service passes on, like basically does another call to another service in the chain, what would happen is that the service will propagate this deadline to the next service and to the next service. So every service next in the chain kind of gets less and less time, if you will, to respond to that request. But this is quite powerful, and it handles one of the one interesting problem when you have client-side retries, and this is kind of cascading retries. So imagine like service A calls service B, calls service C, and then if every hop in the chain does multiple retries, you might get into trouble, right? But with the deadline propagation, this is kind of not an issue because essentially the deadline of the retry kind of controls this whole thing and puts a cap on it. Okay, good, sounds good. We move on, we deploy to AWS. And man, do we feel bad about ourselves. Turns out that there is a limitation of 255 characters. A lot of DNS servers have that. Route 53 is not an exception. Luckily, we can actually split our service config, which is way over 255 characters. We can split it in multiple values to the same TXT record, and then that works. So that the resolver, the gRPC resolver handles that quite nicely. It all works out. And yeah, AWS loves service config, right? It works beautifully. We deploy it to AWS. Everything's amazing. We get our promo or whatever we were after. Our clients are happy. Everybody's happy. We publish this TXT record. It's resolved. The only thing that we need to change is when we configure the endpoint on the client, we need to specify this prefix, DNS colon. That's it. Super simple. And then failure happens. You might sense a trend here. There are a lot of failures in distributed systems, unfortunately, or fortunately. So let's imagine the situation, right? We have 3 clients and 2 servers. And they're all sending requests. Requests are routed round robin, 50-50 on the 2 servers. One server goes down. What happens now is that normal traffic that those 3 clients send now all go to the server 2 because it's the only one alive. However, in addition to that, all the failed requests, like 50% of the previous requests that were sent to server 1, they will be retried because we were smart and we said, okay, we have client retries. We're smart about it. So those 50% will be sent also to server 2, which means server 2 gets 3 times the normal traffic. And server 2 is having a hard time, unless you're super over-provisioned and the server has like 10% utilization usually. If you triple the traffic to a server, it will get rough, right? It might start to time out. It might even crash if you really overload it. And if that happens, at the time it crashes, server 1 actually starts to kind of recover, and then all clients with all new requests and old requests that are being retried, they just start hitting the server 1, which is just woken up from, brought into existence, and server 1 can say, yeah, I'm out of this, like this is not what I signed up for, right? This is called retry storm, and we would like to avoid it. So basically, we want to tell clients when to give up, when not to retry. There is one very popular. How many of you have used circuit breakers? Okay. So circuit breaker is like a distributed systems technique. Essentially, you track failures to certain services, and at some point you might, on the client, and at some point you can say, okay, this server is like not there, so we'll not send requests to it at all. This is kind of the technique. And this is one of the techniques you can prevent, like you can use to prevent this retry storm and allow your service to recover. gRPC has another mechanism, which is pretty cool, in my mind, and probably that's why they implemented it. Essentially, in service config, you can tell your clients what is the percentage of failures that they should tolerate through this retry mechanism. I explained that in lame terms. You can kind of read the documentation that explains kind of the algorithm there. But essentially, it's like I can tell clients, okay, if you see 10%, if you see up to 10% failure rate on my service, keep retrying. Probably we're doing something, but we'll be okay, right? However, if you see more than 10%, stop retrying. And what the client will do, honoring this policy, is that it will monitor the failure rate, and when the failure rate goes above what is essentially described in the policy, it will stop retry. It will still send the requests, But if it sees failure, it will not retry at all, right? This kind of lifts a little bit the pressure and would allow us to exit this vicious cycle of the retry storm. And one more tip of the day, a lot of like those black screens, if you haven't noticed, those kind of my tips for you today. We can actually also tell explicitly clients to back off a little bit and give us some room, give us some breathing room. And a way to do that is you can just include a metadata in the response from the server, but this is like an active thing, so this is now server side. And you can say, hey, I'm still kind of rebuilding my cache or whatever. I need more time, so don't retry in the next, let's say, 5,000 milliseconds or 10,000 milliseconds or whatever. Okay, we're back in the game. We get the next promo. We're now whatever level 20 fighter in our company, and everything works beautifully. But then, guess what? Failure happens. And this failure is like sneaky one. We see timeouts. Okay, and they're clearly transient. So there is like request fails due to timeout. The retry doesn't help. So there are retries, right? We made sure. It doesn't help because it timed out. It just uses the whole time, like one single request uses the whole time budget, if you will, for that call. So retry doesn't help. So those errors, the users see them. They pop up on their phone or on their browser, whatever. They see those errors. And they're not a lot, but it's super irritating. And we're embarrassed because we have this robust retry mechanism, and we built our promo case, and everybody tapped our shoulders because we're such an amazing engineers. And now, like, clients see errors, and they ask us why, and we don't know. So we start this troubleshooting journey. We look at the debug network in AWS. We look at our metrics first, right? Our metrics, our black box metrics, our saving line. And it doesn't help us because when you look at those metrics, there are no timeouts. There is no latency increase. AWS Load Balancer says, yeah, all good. Everything's working. But the client says, no, I see an error. Here is a screenshot, right? So what we do, we can debug gRPC with environment variables. So I can go into even the live environment. I can set some environment variables enabling some debug logs. And I can actually look at the life cycle of gRPC. And I can understand a little bit better how this thing works on the inside. So how does it work on the inside? So we have essentially changing the prefix when we configure the endpoint, the server endpoint. What we did is we changed the resolver. So there is this component that is called a resolver. And what it does is it needs to discover the IPs, essentially, where requests will be sent to. And by default, this resolver, when it discovers those IPs, it sends those IPs to the load balancer, which is a component on the gRPC stack. And by default, this load balancer is picked first. And it's a super simple and super elegant idea. I have 3 IPs. I get the first one. If I am able to connect to it, that's my guy. I just start sending requests to it. However, what we notice in the live environment is that sometimes when the application load balancer kind of does some like auto scales or removes an IP, this thing doesn't work. I mean, it just still connects to the IP that is gone, and it times out. So it turns out that when application load balancer in AWS goes away, it doesn't really go away. You can still establish a TCP connection to it on the same port that you used before, so it kind of seems lively. You cannot really establish, like, you cannot, like, the state that the gRPC channel subchannel gets into is connecting. So it says, okay, this guy accepted my TCP request. I don't get the HTTP2 kind of handshake with settings, but it's definitely somewhere there. But there is nobody there. That's why he tries to send a request through that connection, and it doesn't work. It just times out. And then when failure happens, what happens is that the connection failure would inform the DNS resolver to refresh the DNS resolution and see that, okay, this IP is no longer relevant. And then it removes the IP, establishes a connection to the new IPs, and then everything works. But yeah, those timeouts are there, and we don't want them to be there. So we can round robin for the win. So the default load balancer doesn't play nicely with the schema that we have, right? So we need to change it to the round robin one. And it's a client-side load balancer. So what does it do? So chances are, if you're running any significant load, AWS load balancer will have more than one IP. And with the, if you're running multi-AZ, again, you have more than one IP. And what this will do is it will, use all the IPs in the DNS record. But there is more. It will establish a subchannel for every IP, and it will essentially monitor this channel. So it will not send requests to a channel that is like connecting. It will wait for the channel to be ready, so that like a little handshake with the settings is done before sending any request to it. Even more, we can actually use client-side health checks. So gRPC has a standard health check API, which is a gRPC API. So gRPC kind of extends the protocol with gRPC, which we can implement on the client, on the server, sorry, and we can instruct the client to honor in the service config. And then we're sure not only it needs to establish the HTTP connection, for sure, not only the TCP connection, but it also should see that the server is healthy in order to send requests to it, which is perfect, right? Exactly what we wanted. And then, no failure this time. There is no failure. Our system is hyper-resilient, and it works all the time. However, there are some spikes in the traffic, and what we do and what AWS does, it scales horizontally the application load balancer. However, if you follow through how this DNS resolution works, so basically, when I ask the DNS server, okay, give me the IPs, it gives me 2 IPs. Until I see a failure, I will not ask again. And if there is a new node, new instance, you know this joke, when a tree falls in the forest and nobody hears it, it did fall. Right? Basically, if there is a new application load balancer and nobody hears about it, is there a new load balancer? And the answer is no. So what we can do, what can we do, right? Well, we need to make failure happen. By default, and here I'm not 100% sure about all the languages, but Golang for sure, and I'm pretty sure most of them, by default, there is no max connection age. So a connection established between client and server might live forever, or at least for a few hours, so you might not get a chance to see that there is a new instance. So setting this max connection age, and this is not service config now, this is kind of a configuration on the server, so this is part of the exchange between the client and the server, the settings handshake that I mentioned. This would inform the server that, okay, we'll make sure that no connection lives more than 5 minutes, for example. And if you do that, this will essentially cause the client, when this connection is gracefully shut down by the server, when this timeout is up, the client will see the go away and say, it's so like graceful shutdown, I should check out what's going on in the DNS and discover the new IP. Cool. We are almost there, and this didn't refresh. Okay. Okay, we're pretty solid now. We have our auto-scaling, everything works, and we know what to do, right? We focus so much on transient errors, but what should we do with non-transient errors, right? And again, industry wisdom. Server errors, client errors, this is kind of the generic classification. From HTTP terms, you might be familiar with this kind of 500 versus 400, right? So 500, yeah, sorry, we're terribly sorry about this, we're working on it. And then 400, you're stupid, what are you doing? Like bad request, right? And gRPC has the same concept. You can say invalid argument, you can say precondition failed, essentially telling clients, yeah, this is like, you cannot ask me to do that. Right? This fails because of you. It's your fault. And what we do as a service owner about those errors, we can just ignore them, right? Because it's not our problem. It's client's fault. They're stupid. And clients don't agree. Clients think that they're smart, and they actually are. And they need to figure out what to do with those errors that we send to them. And what would they do, right? What can they do? Well, they can come banging on our door, or if you're open space, they can just come by the desk and say, hey, I see this error. What the heck is going on? And then we explain, and they are smart people. They understand. And they, okay, I got it. And they go away. And then a new engineer starts on the client team, and they see this error, and they come knocking on our door and say, hey, what's going on? So like this is a vicious cycle. Like we want to break, we want the services to talk to each other, like we did with the retries, not like engineers like explaining to each other what this means. And how to do that? So error propagation, if you will, in gRPC works in the following way. There is a very simple and robust mechanism that works most of the cases, which is when an error happens, we can construct, we return a code and a message. The code is like those codes that I explained, and the message is developer oriented. So this message is not intended for like somebody to see it on their phone. It is for the developer looking at logs to understand what's going on. And there is another, like this might or might not be enough. If it's not enough, if you have like more complex API, let's say you have invariants in the API, in the API object, in the API request that you cannot express with protobuf. I mean, protobuf is pretty amazing language, but it cannot express complex business logic into the request that you cannot, I don't know, you shall not credit an invoice that is in draft mode, let's say. It's still draft, right? It kind of doesn't make sense. You can only credit an invoice that is issued, whatever. Those things you cannot capture really in the API schema. So you need some way to let clients know what went wrong, and ideally do it in a machine-readable way, because they might need to surface some message to their clients, which will ultimately, propagating through teams and services, can end up on somebody's phone saying, we're still processing your payment, please stay put. If the problem persists, please call support. And how does, so again, gRPC extends with gRPC. There is we can essentially create a protobuf message, part of our contract, that it represents the error structure, the machine-readable error details. And when we are returning this status to the clients, this error which says, okay, invalid argument or failed precondition, we can put this object that describes in a very strong schema way what exactly went wrong. And we can have this contract established with our clients. They can process it. We can go to the extent where the client, like website, for example, can display like next to the field exactly what the problem is. For example, okay, I don't know, you cannot have been born in the 1500s. Like this is not, we don't buy it. And this is something that you can propagate through that mechanism. There is, I don't have a black screen for that, but I'll share it anyway. There is a Google API's standard error details that are generic and they're modeled around the status codes, which you can use kind of out of the box if you don't want to come up with your own error structure. So there is that. How is this encoded? So those details are encoded into an any structure. This is a protobuf term. It's a well-known type in protobuf, which has type URL and the bytes, actually, the message. And on the client, if the client has the schema for that type, they can essentially reconstruct the message. So it's like one of the extension mechanisms that it's kind of built on top of protobuf and gRPC. And what you can see here is that this works across languages. So we are not restricted. We can have a client side or like a backend for the front end, whatever, that is written in Node.js, and they have a Golang backend services, and they can talk and understand each other and they can use the same mechanism. Important tip, always, and this is like you cannot avoid that. Errors are part of your API. If you provide more details with the errors, people will use that detail. It's part of your API. But when you do that in this fashion, when you put it in the schema, at least it's super obvious that that's the case. Otherwise, if you give very little information, you start this kind of off-the-record knowledge sharing, which is not scalable. Yeah, so at the end, what we have the service chain, we have the load balancers in between, we get all these cool features, it's polyglot, client retries, service owner can control those policies, we have the health check and machine readable error details. And yeah, just to know, nothing is free in this life. There is no such thing as free lunch. There is overhead when you have components between your services. This is actually a benchmark that we did. I mean, it's not super scientific, that's why I haven't shared kind of super detailed, but there is overhead. So having a load balancer between each service, or having like a service mesh, whatever, might be your thing, might not be your thing, really, really depends. So just be aware there are trade-offs, always. And with that, I thank you for coming, listening in.
So do you have any questions for Kiril? There's one hand raised. And we kindly remind our people who are watching this live stream, they can ask questions there.
Should it appear here?
Yeah.
Okay, cool.
Probably.
Oh, good.
assembly language, right? And now I don't think that too much people are doing that. Then we have something else like C++, and also a lot of people talk that, but not right now. I see some hard-coded numbers like 5 seconds retry, also some hard-coded things. And my question is, how long will it take for us to make such a communication between services that they can do it automatically without our little configurations? If I made myself clear, thank you.
It's a very open-ended question. I don't know. A lot of this, let's say, communication layer is not new. It's been around for decades, even longer. If you look at the networking stack, it's been like since the invention of the internet, even before that. So there is like a lot of low, and also there, when you talk about communication, any kind of fuzzy kind of approaches to it usually are not the go-to approach, because you want many use cases require predictability, if you will, and we have far too many things like garbage collection that are kind of or non-real time, like multi-user, multi-process systems, that is hard to control this, make this predictable. So I don't know really. I think it will not be soon.
Any more questions now? We kindly remind you that you can find Kiril in the next coffee break in the speaker's corner, and he will be eager to answer any of your further questions. So let's thank him one more time. Big applause for Kiril Vuchkov!